So we've been talking about entropy. Remember, entropy is a measurement of disorder or randomness, represented by the letter S. Now, we said that the second law of thermodynamics said that a reaction is going to be spontaneous if the entropy of the universe increases. Everything is moving towards more disorder. So what we're going to be doing is we're going to be looking at chemical reactions. Now, temperature and pressure are two things that affect our randomness or our entropy. So initially, we're going to hold temperature and pressure constant, and then we'll see what happens when we change that out, okay? So when we have a reaction, if we've got gaseous molecules, the more molecules we have, the more entropy we have. The number of molecules determines our randomness. So in this case, I've got 4 plus 5, 9 gaseous molecules over here. On my products, I've got 4 and 6, 10 gaseous molecules. So my products are going to have more entropy. So this reaction would be favored in terms of entropy. Okay? Now remember, entropy is determining randomness. The change in enthalpy, which was our H, is talking about our heat at constant pressure. It tells us if the reaction is endothermic or exothermic. Neither entropy nor enthalpy alone tells us if a reaction is spontaneous. It's the change in free energy, which is our letter G, that's going to tell us if a reaction is spontaneous. Remember, a negative change in free energy is going to be a spontaneous reaction. A positive, under those conditions, won't occur. Okay? So when we talk about entropy, entropy is disorder. Now at 0 degrees Kelvin, it's absolute zero. All motion stops. So for a solid, if it's a pure crystal at 0 degrees Celsius, there is 0 degrees Kelvin, big difference. 0 degrees Kelvin, there is absolutely no motion, no vibration, no randomness, and our entropy is actually 0. This is only for a solid at absolute 0, 0 K. As soon as I start heating it up, my atoms or my molecules are going to start to vibrate in place. And if you notice, it's only a small change, but it's there. It's no longer neat and orderly and organized and 100% straight, so now I've got a little bit of randomness. Now I've got a little bit of disorder. Now I've got a little bit of entropy. Okay? So as the temperature is increased, our disorder increases. You can say disorder or you can say the vibration. Both are true. And that means our entropy is going to increase as well. Okay? Now, because entropy values are temperature dependent, anytime you see this little superscript of a 0, that's telling me I have standard temperature and pressure. Standard temperature, in terms of entropy, is 298 K, and it's going to be 1 atmosphere of pressure. Now, when we're looking at entropy, we have this reaction that should look very, very similar. We've seen this exact reaction before for delta H. To determine the change in entropy for my reaction, I'm going to take the sum of the number of moles of each of my products times the entropy value for each of my products given to me in a table. minus the sum of the number of moles of my reactants times their S value for my reactants. Okay? So here, I've got my reaction. I want to calculate delta S. So I want to find the sum of my products. So my products, I've got 2 times SO2. SO2 is 248 joules over K dot mole, plus 2 times NiO. NiO is 38, minus the sum of my reactants. So my reactants, I've got 2 times NiS. NiS is 53, plus 3 times O2. O2 is 205. So when I plug this in, I've got 2 times 248 is 496, plus 476, 2 times 38. Okay? That can't be right. Let's make that 76. That's better. Minus the sum of my reactants. 2 times 53 is 106, plus 3 times 205 is 615. Okay? So then I'm going to tally these up and subtract. And I'm going to have to redo that calculation because I messed that up. So 496 plus 76 is 572, minus 106 plus 615 is 721. So 572 minus 721, and I get that that's negative 149 for my delta S. Now my delta S has to have units. All of my units are in joules over K. Now this is times mole, but that's what all of these are. These were my moles, so that goes away. So I'm going to have negative 149 joules per K. Okay? So that's my change for delta S. I can actually put that there too. So take a second, solve out your delta S, determine how much that's going to change for the reaction given here. Remember, it's the sum of your products minus the sum of your reactants.